Today I'd like to talk about two features of replacement analyses. We saw in an earlier lecture that in replacement the problem is slightly different from assessing independent alternatives or mutually exclusive alternatives for a problem, because we're replacing an asset you currently have. Now, one of the complications of this is making sure one chooses the correct figures in the replacement study. And secondly, the idea of cyclic replacement, where we're buying the same asset over and over again. So those are two topics of today's talk. First, the correct choice of values. I have a problem here involving Clem buying a computer. We have a number of bits of information about Clem's computer purchase. The fact he has one that he bought 3 years ago, which he can now sell in the open market for $300. The local Mr. Computer store will sell him a new HAL computer for $4,000, which includes an accounting package he wants. His own computer will last another couple of years and would then be worthless. The new computer would have a salvage value of $300 after 5 years, and the net benefits to Clem of the new accounting package and other features of the new computer amount to $800 per year. Now we also have an additional feature that Mr. Computer, the Mr. Computer store, will give Clem a $500 trade-in on his current computer. We're given an interest rate and asked what should Clem do. So in these kinds of replacement analysis, you recall that we have two problems to deal with. One is whether the asset should be replaced, and the second one is when. Now, we're asking this problem, what should Clem do? So we'll be looking at both, perhaps simultaneously. But first, the issue is whether, in fact, the computer should be replaced. Now, we've got a Defender, which is the computer that Clem currently has, and a Challenger, which is the one he's going to buy. I'll break the cost down again into operating costs and capital recovery. In the problem, we saw that the benefits to Clem of the new accounting package and other features of the new computer amount to $800 per year. So that's a benefit of the new computer, which can also be considered a cost of retaining the old computer. I could put that in as either a negative cost for the new computer or a positive cost for the old computer. And just for conventional purposes, I'll put it in as an operating cost of the old computer. We also have capital recovery. And in this case, what we want to look at is the worth of his current computer. In our problem, we're actually given two possible ways of determining the worth. We say he can sell the old computer in the open market for $300, or Mr. Computer will give him $500 trade-in. Now, the worth here to use is really the open market worth. The fact that Mr. Computer Store is giving him $500 is just an inducement for buying a new computer. It doesn't really measure the worth of the old one. The best measure for the worth is the $300. So we'll use the $300 figure in the capital recovery. So it's $300 times the capital recovery formula at 15% over the 2-year life of the old computer, and that works out to be $185. For a total annual cost of the old computer of $985 per year. For the Challenger, the operating cost, because we put the $800 in benefits as an operating cost to the Defender, is 0. And the capital recovery is a little more complicated. I'll use the capital recovery formula here, which takes the current value and subtract off the salvage value. Let's have a close look at what that current value is. The problem statement says that the local Mr. Computer store will sell him a new HAL computer for $4,000. So intuition would say, well, the price of the new computer is $4,000. But let's look a little more carefully at this. In fact, the price is more complicated because of this feature of a $500 trade-in on his old computer. We know his old computer is actually worth only $300. So that extra $200 comes from somewhere. And where it comes from is actually lowering the price of the new computer. The Mr. Computer Store is giving a $200 inducement to Clem to buy the new computer. That $200 inducement is really saying, well, the price of this new computer is really only $3,800, not $4,000. That's what the extra $200 means. That's where it comes from. So the correct value here, the best estimate of the worth of the Challenger is not $4,000, it's $3,800, from which we then subtract the salvage value of $300, multiplied by the capital recovery factor over the 5-year life of the new computer, adding the salvage value times the interest rate, giving a result of $1,089. So the total annual cost is $1,089. So the answer here, of course, is that Clem should keep his old computer. The annual cost is less over the remaining 2 years of life. So we don't need to look at when to replace the Defender as well. The important point here, the point in this whole example, is the correct choice of values for the worth of both the Defender and the Challenger. The Defender here, actual worth is market worth, not what is bound into some kind of other arrangement. The worth of the Challenger here is $3,800. If Mr. Computer Store is willing to give an extra $200 on the trade-in for Clem's computer, then he's probably willing to sell the computer for $3,800. So it's the better estimate of that value. So it's kind of important in these capital recovery calculations to make sure one gets the correct value for these assets. Now the other complication of replacement analysis I want to look at is called cyclic replacement. Here you have an asset in which the asset is replaced by one exactly like it after a certain period of time. So something that wears out fairly frequently. Some tool perhaps that's used until it wears out and replaced with a new one. And the problem is simplified a bit because you're always replacing an old asset with one exactly like it. And you can work out in advance how often that's to be replaced using this little rule here, that the economic life of the asset is equal to the least cost replacement interval. Now I'll explain that rule with respect to a problem. Here we have some tool, a rotary Snorf dribbler. And it's worth $9,500 new. We're given a minimum acceptable rate of return and interest rate. We want to know how often the Snorf dribbler should be replaced. And we're given a lot of information concerning its salvage value after a certain number of years and the operating costs of the Snorf dribbler during each year of its life. Now we can see that, as one would expect, the salvage value diminishes the older the asset gets. And the older the asset gets, the operating costs increase. It's harder to maintain, just like an old car. It costs more to maintain than a new one. Now the logic here is that as the asset gets older, its annual cost does in fact increase because its maintenance costs increase and its value in terms of salvage value decreases. So there comes a point in its life in which it's better to replace it with a new one. That point in its life is when the average cost over whatever period of time that is the smallest. So what we do to solve these problems is simply create a list of the equivalent annual cost, that's what this column is, associated with each possible period of time that the asset could be kept. So if we're keeping this for 1 year, the equivalent annual cost is $36.40. For 2 years, the equivalent annual cost is $33.19, and so forth. So let me do an example calculation to show where I got this. Let's look at the 3-year life, just as an example calculation. What we have is the components of operating costs and capital recovery. The capital recovery will be the first cost, $9,500, minus the salvage value at year 3, it's an example calculation, is $6,000, right? Times the capital recovery factor of 12% for 3 years, because this is under the scenario we keep it for 3 years, plus the salvage value times the interest rate. Plus the operating costs. We can see the operating costs are at least $1,000 each of the years, so we can just add $1,000 here. At the end of the third year, we have an extra $200, which will spread over the 3-year life. Giving us a total annual cost, and it works out to be $32,3650. So that's just a sample calculation of one of these rows. So there's actually a lot of calculations hidden in this little chart. But if you look at these equivalent annual costs, they diminish until we get to this point here. And then they start increasing again. So the idea is if we plan to keep this Snorf dribbler for 2 years and then replace it, and keep it for 2 years and replace it, a cycle like that, it's going to cost us $33.19 a year. If we cycle on a 5-year basis, keep it for 5 years and replace it, then on average it's going to cost us $32.90 per year. And if we replace it more frequently than every 5 years, it's going to cost us more on an annual basis, and less frequently than every 5 years, it's going to cost us more on an annual basis. So we want to replace this every 4 years. That should be, of course, because the 3233 is the cheapest in that list. So it's every 4 years we want to replace that Snorf dribbler. The minimum equivalent annual cost for each possible number of periods of replacement. So that gives that economic life. We can say, as we've said in previous problems, the service life of an asset is X years. We can actually calculate that through this kind of a process of calculating the cyclic replacement interval as the least cost one. So in this talk, those 2 points: making sure we're using the right figures for replacement cost calculations, and then figuring out the economic life of an asset using the least cost replacement interval. Thank you.